immediately tell me that there is a lag, okay? Uh, 1 second. Okay. Okay, tell me one thing. How would you like your final exam to be? What is the general consensus on that? Did you guys have a vote yet
On.
on the final exam?
So what are the possible options for the, I mean, who are the contestants for the vote?
Well, it's an illusion of democracy. I want to know what you guys will prefer. That's how I would like to put it. Okay. What would be a convenient form for you guys?
No exams, A plus for everyone.
That will cost me my job, so I can't go there. So we'll have to make a compromise on that front.
I think anything that would, give us enough time to think and write would be nice, because in some places we are just having to hurry through and, yeah, just enough time to answer questions is asking for a lot in some cases.
Yeah, I mean, in some of the papers, what is happening is basically it is becoming a speed test. Like we have to answer, say, some, like unimaginable number of questions in some 2 to 3 hours, and it's all
Yeah,
becoming a speed test in order to ensure that there, we understand what the professors are trying to do. They are trying to ensure that there is less cheating and all of that. But for
Yeah.
that, they are giving an unimaginable number of questions, which it's not possible to even answer properly in that particular interval.
Okay.
so maybe,
Uh,
questions, good questions, but lesser in amount and with sufficient amount of time to answer them would be nice. Because I'll give you an example. In our physics midsem, I had to write continuously for 5 hours. And
okay.
yeah, in our physics lab, we had 2 hours to answer, but there were about 25 questions, and they had to increase the time to 3 hours so that we could finish writing. And still, it was a speed test. So,
And you are not giving the
Yeah, like
exams
25
in
questions in
person,
each,
right?
it got some three subparts.
Hang on, Shukriya, hang on. So none of you are giving the exam in
Yeah, we're
person.
not
You're
giving
giving it.
exam in person. None of us are
No.
invited back to campus yet.
Oh, okay. So usually my exams are open book exams, and okay. So okay, we'll figure something out. Instead of going for quantity, we'll go for quality, and mm, there will be some descriptive ones where essentially you have to know what is what. Other than that, it's going to be mostly numericals or derivations. So uh, hopefully you'll be able to do that. Okay, we'll sort it out. Don't worry about it. Okay.
and sir,
Uh,
has it been
yeah.
decided whether the previous modules portions would be
There
included
will be some from the previous module. I'm coming back to Bangalore to on Sunday. I'll sit down with the other instructor, and we'll come to a decision where which bit of his module we will keep. Um, what was the most interesting bit in his module? Don't tell me nothing. Give me something to play
There
with.
was a particular portion which wasn't covered for our midterms. I think like about after sedimentary rocks, that wasn't there for the midterms. So yeah, but I think everything was equally interesting.
That is a very dangerous answer. Um, well, everything will be equally interesting. You're not quantifying the level of interest. So, anybody
think of it
else
in
wanna
another way. It's
pitch
an
in?
incredibly safe answer.
It's an incredibly safe answer. And uh, what would be given an honest view? What would be which sections would you think that you will prefer to work with? Nobody? Okay,
I
then I
feel
will
like
sit.
again it's very personal, right? I
Yeah.
personally enjoyed the fossil oriented paleontology part
Okay.
and like how like what sort of information we got from that. But again, that's personal opinion.
That's personal, but that's good. I've got one number to play with. Anybody else?
Yeah, I
The
really
part
like
on
the rock cycle part.
Okay.
To be honest, not a lot of things that he taught were interesting, honestly, but I think that part was relatively better. Yeah.
Okay. Anybody else?
I like the part on the origin of life. I mean, the stuff that he had covered about, Sutherland's experiment, etc., the stuff on origin of life. That was like some bit of interesting, the chemical origin, I mean, the abiogenesis and stuff like that.
Did he go through the Miller-Urey experiments and stuff like
Yeah,
that?
yeah, yeah,
Yeah.
Yeah.
yeah,
Okay.
yeah.
Fine. Okay. That gives me some direction regarding how to play with it. I'll take a decision probably early next week and let you guys know. So we'll take it from there. Okay? Okay. Let's get to class.
So, sir, just a confirmation. So it's confirmed that there'll be a exam, right? I mean, a timed exam.
There will be a timed exam. I'm trying to negotiate with the UG office whether we can do a slightly more flexible one, because you guys are sitting at home and it's online, so it shouldn't be a too difficult proposition. Instead of bombarding you with questions, I can give you more difficult questions which takes times to answer. So fewer but better questions. That's what my approach will be. But hopefully, I'll get a positive answer from the UG office. Okay.
Okay, sir. Thank you.
Okay. Sure. Slides visible?
Yes, sir.
Yes, sir.
Good. So last lecture, we looked at the primary production around the world. The primary production is nothing but biology kicking in and taking carbon dioxide from like if in terms of marine production, they take the dissolved carbon dioxide from the bicarbonate form, utilizes nitrate and phosphate to form organic matter. And this biology has kind of shaped the planet. Why do I say that? We talk about the terrestrial forests and everything as a carbon sink, but keep in mind that 60% of the oxygen of the atmosphere is coming from the marine ecosystem on an average basis, and in times when when the ice caps are melted, the planet is in a hothouse condition, 80 to 90% of the oxygen is coming from the marine system. Okay. And the marine reservoir contains 90% of the surface carbon cycle. What do I mean by the 90% of the surface carbon cycle? There is the surface carbon cycle, which includes the atmosphere, the biosphere, the terrestrial soils, and the oceanic system. And then there is the deep carbon cycle, which is the mantle, the inner part of the earth. Mantle has so much carbon that we don't even want to go there. But among the surface reservoirs, the marine system, especially the deep marine system, contains 90% of the total carbon present in the entire pool. So how organic matter is formed, how the organic matter is respired, how it survives respiration becomes a very important factor, because formation of organic matter, because this CO2 in the seawater is diffusing in from the atmosphere. So if I keep producing organic matter, I will keep reducing this CO2 concentration, and thus, in a way, I'm going to create a gradient between atmosphere and ocean. More CO2 from the atmosphere will diffuse into the ocean, and the atmospheric CO2 concentration will drop. And in the previous lectures, we have seen that CO2 plays an important role in terms of greenhouse warming of the planet. So if we can manage to draw down the CO2 of the atmosphere by increasing marine productivity, by pumping the inorganic carbon dioxide into organic form and transferring it from surface ocean to deep ocean, we're going to cause a global cooling. So a lot of scientists have theorized that a good way to mitigate the global warming problem is to fertilize the ocean. What do I mean by fertilize the ocean? It comes from this concept that most of the ocean is limited by the nutrient availability. What we are looking at are the constituents of seawaters. We have done this in the previous lecture. And there are different kinds of depth profile we observe in seawater for different elements. Example is boron, which is a bio-unlimited element. It has nothing to do with biology, or even if it has something to do with biology, it's present in such a high concentration that no matter how much biology happens, its concentration is not impacted by biological activity. The other component is the carbon, which we are interested in because CO2 transfer from surface to deep is essentially a sink of CO2 from the atmosphere and thereby can lead to global cooling. What you can see is that in the surface ocean, there is a depletion in equilibrium CO2 concentration from what it should be, but through simple diffusion mechanism. This depletion is a function of this, what we were observing, inorganic carbon being converted into organic matter. So, as scientists, we term this particular kind of profile as a biointermediate profile. In terms of biointermediate profile, the surface ocean is depleted with respect to the deep ocean due to biological activity, but the depletion doesn't go completely to zero. The other element, which is of critical importance, is nitrate as well as phosphate. You can see silicate. These elements are quantitatively depleted in surface ocean. That's why they become biolimiting elements. So in most oceans, CO2 is unlimited. There is essentially as much CO2 as you want. You can keep diffusing from the atmosphere. However, nitrate and phosphate, they are taken up from solution, converted into particulate form, that is organic matter, and they sink to the bottom of the ocean. Now, biology wants to keep this nitrate and phosphate back in suspension because they can utilize it to have more primary production. So there's a constant production respiration cycle going on, and that is what we're going to cover in today's toolbox model. Going from nutrients to we have the bioactive gas, which is essentially oxygen, which is being utilized for respiration. And the profile tells you in the surface we have diffusing in. There's a slight increase in subsurface due to photosynthesis, and there is a sharp decline below the photic zone or primary production zone due to respiration. Okay. Now, we start with a nutrient profile. We are looking at phosphate and silicate concentrations with depth. Depth is given in meters up to 5,000 meters. The silica concentration is in the bottom x-axis and the phosphate concentration and the nickel concentration on the top x-axis. And this is from North Pacific Ocean. And you can see that both the nutrients are quantitatively depleted in the surface. So in this surface ocean, if I can supply with more phosphate and nitrate, I can have more biological productivity. I can transport more carbon from the surface to the deep, and thus allowing carbon dioxide from the atmosphere to diffuse into surface seawater because there is a concentration gradient away from equilibrium, and thus leading to a drawdown of CO2 from the atmosphere. Now, in terms of the organic matter that is produced, it follows the Redfield ratio, which means that the carbon to nitrate to phosphate and to silicate ratio remains constant all across the globe. Because the generic formula for organic matter includes carbon, nitrogen, and phosphorus in 105 to 15 to 1 ratio. This ratio has been revised, as we have seen before, but we're going to play with this for now. The hard parts, the shells that we form, the calcium carbonate, the silicon dioxide, they have a calcium to carbon ratio of 1:1, that is 26 to 26, and then silica of 50, and gives you a generic flux value of this. Okay. Now, from there, we know that nitrate and phosphate all across the globe are very tightly correlated because either they have been utilized by biology in the same proportion or produced by biology through respiration of organic matter in the same proportion. That is always 16:1. So if you take a seawater sample from anywhere in the globe away from a large river, so large rivers can change this ratio, However, if you go to the open ocean, any upwelling zone, take a sample of seawater from any particular depth and measure the nitrate to phosphate concentration ratio, it will always be 16:1. It's totally dominated by biological cycling. Just a quick overview, we saw that in the hard part formation, calcium plays a role. However, there is a lot of calcium in seawater. The concentration is 10 millimolar as compared to phosphate nitrates, which are in micromolars. So there is 3 orders of magnitude difference in concentration. So even with a lot of biological activity, calcium concentration can be perturbed by only 1% or less in the surface ocean. As we can see that the surface ocean has slightly lower calcium concentration than the deeper parts of the ocean. So we can't really call it a biointermediate element. However, it's still important to note that the calcium concentration can be perturbed. Now, this is our primary productivity. We know that the gyres have zero productivity because there is no nutrient supply, there is no dust supply to these gyres. Coastal places have high productivity given in very high amounts of carbon flux in gram carbon per meter square per year. Upwelling regions have very high productivity because you're bringing up deep nutrient-rich waters from the abyss. So from that perspective, we know that the fall in organic matter gets respired. The respiration utilizes a series of electron acceptors, and the series of electron acceptors goes from oxygen to nitrate to manganese +4 to iron +3 to sulfate CO2. And why does that happen? And this is the series of respirations we can have. Aerobic respiration is driven by oxygen, nitrate, then comes manganese +4, iron +3, then sulfate, then it's methanogenesis. And this is utilizing a generic formula for organic matter, which is given by this formula: CH2X, NH3Y, and H3PO4Z. Okay. The entirety of the reaction series is driven by the Gibbs free energy of the reaction, and which is dependent on the half cell potential of each of these oxidants. Okay. Oxygen obviously has the highest energy available for a half cell reaction, and the least is through sulfate to sulfide. Okay. Obviously, methanogenesis sits in the bottom, and it is the least preferred mechanism we have in the world. Now, if we break up the oceans into surface ocean and deep oceans, this is what we observe. The surface ocean, the top 500 meters to a kilometer of the ocean, is where we have sunlight. So this is the only place where we have primary production. For now, we're going to ignore the deep sea vents. Last lecture, we saw that around deep sea hydrothermal vents, we have some primary production, but that primary production is not significant enough. What's happening in the surface ocean far dominates the carbon cycle of the globe. The input to the surface ocean is classical river input. We have a value of total river flux, globally averaged. We know what is the flux weighted concentration of river water of a particular element. In terms of water, we can have evaporation and precipitation in surface ocean. And in the surface ocean, when we form the when biology kicks in, we form particulate matter. Calcium carbonate shells, which has organic matter inside, radiolaria, coccoliths, foraminifera. These are all surface-dwelling primary producers or secondary consumers, which will take up nutrients, which will take up calcium, which will take up carbonate ion from the seawater to form their hard tissue, to form their soft tissue. As we covered in the first lecture, that there is downwelling of water at the poles. We know the North Atlantic Deepwater Formation and the Antarctic Bottom Water Formation, and then there is upwelling of water, sometimes wind-driven due to Coriolis effect along the western boundaries of continents, and at times due to the thermaline circulation around North Pacific. So there is some amount of water going down, there is some amount of water coming up. And this falling particulate matter will get remineralized or essentially respired by bacterial activity or consumed by secondary feeders, tertiary feeders. So they're going to get back into solution, which is kind of the fraction of the total particulate matter that falls gets back into solution, and a small fraction will survive this remineralization and fall into the bottom of the ocean. Last but not the least, we have the hydrothermal circulation. Hydrothermal circulation has zero impact on the water budget because this is deriving water from seawater, and that seawater is circulating back into the deep ocean. The chemistries are very different. What goes in and what comes out are very different from one another. We had seen that in previous lecture. The percolating seawater reacts with the hot basalt. Magnesium is removed from it, calcium is added to it, sulfate is removed from it, sulfide is added to it. A lot of transition metals are leached from basalt. So this is a complex system. However, the net water budget of this system is zero. What goes in comes out. Okay. So if we summarize the two sections of the ocean, the surface ocean and the deep ocean, and we put together the input parameters and the output parameters, this is how we will get it. Surface ocean, we have precipitation. That only impacts the water budget. We have the river runoff, impacts both water and concentration. We have dust, purely impacts concentration or the flux of material to the surface ocean, and the upwelling of deep water. If the surface, if the CS and CD, the concentration of a particular element in surface ocean and the concentration in the deep ocean are different, right? If it's not a bio-unlimited element, right? Bio-unlimited elements have constant concentration with depth. So upwelling or downwelling of a parcel of water will not impact the profile or the concentrations in each reservoir of a bio-unlimited element. However, if it's a bio-limiting or a bio-intermediate element, we know that the surface ocean will always have far less amount of that particular element than the deep ocean. So upwelling will essentially be an input of that element to the surface ocean. Now keep in mind, for an element which has a strong dust input, like iron, like aluminium, upwelling will not be a source. Upwelling be the downwelling upwelling component will be reversed in this case because the surface ocean has a lot higher concentration than the deep ocean for elements which are dominated by dust input. Please note that in the exam, I'll give you problems which talks about elements which will describe the cycle of the element in seawater, and you will have to draw a two-box model of it. So you will have to recognize that this element will have a surface input or a higher concentration in the surface, a deep input or a deep concentration in the surface. Okay, so keep that in mind. The output terms simply is evaporation, only impacts the water budget. Biology, the main thing. The downwelling of surface water, it's moving material away from surface water, and then there is the particle scavenging part. We're going to quickly cover the particle scavenging part in the next slide. The deep ocean is a bit more simpler. It's getting water through downwelling of the surface ocean. Then there is the hydrothermal circulation. Please note that for water, it's zero net flux. For few elements, it's an input term. Elements like calcium transition metal, it's an input term. And last but not the least is the benthic boundary flux. It is the diffusion and advection of water from the sediment column into the seawater. Okay, so that flux remains, for a unit area, that flux is very slow or very small. Sorry, not slow, very small. However, if we look at the entire ocean, we are looking at millions of square kilometers. So that flux becomes a huge flux over a 1,000-year to 10,000-year to a million-year time scale. The output flux from the deep ocean is the upwelling of the deep water. For bio-intermediate and bio-limiting nutrient elements, this is very important because the deep ocean has a much higher concentration than the surface ocean. There's the hydrothermal circulation. For magnesium, say, it's an output flux. For what else? For sulfate, it's an output flux. And last but not the least is the clay formation, like orthogenetic precipitation of clay minerals. This is a very slow reaction that happens at the sediment-water interface or sometimes in the sediment column, where inorganic components come together to form clay minerals. Okay. We are not going to get into the details of it. Particle scavenging is something that we didn't cover in the last lecture. Particle scavenging is, yes, go ahead.
So in the last slide, you had the word orthogenic. So what is the meaning of that exactly?
In situ. It happens orthogenic. So in the oceans, there are two kinds of clay. One is a detrital, one is an orthogenic. Orthogenic clay is precipitated in the ocean at the bottom of it. The detrital clay is the clay that has been transported by river. Is that clear?
Yes, sir.
Okay. So essentially, if you are precipitating calcium carbonate in a beaker, that's an orthogenic precipitation. And if you grind up a chalk and put it on it, it's a detrital fraction. That's how we are differentiating what's forming there and what's being transported to there. So particle scavenging plays a very important role for transition metals. Essentially, if you have an unfilled d orbital, okay, you are essentially highly attracted to any charge, any electron that you can grab onto. So any transition metal or rare earth elements will love to be associated with a charged surface. Organic matters are at times charged, silicon dioxide lattices are at times charged. So anytime you find a system like that, you're going to jump onto it. The other part to keep in mind is that iron is soluble in +2 form, but in +3 form, it's quite insoluble. The solubility is also a function of pH. When rivers bring material to the ocean, their pH is usually less than 7. Okay, it can range between 6 to 8. Some rivers are known to be higher than 7, like the Ganga River. However, most rivers are slightly, I would put it on the acidic side, slightly less than 7. So iron remains soluble, comes to the ocean. As soon as it hits the ocean is at a pH of 8.3. So it's going to form ferric hydroxide. Same is true with manganese. So all these elements, all these transition metals which have been in solution in rivers due to its lower pH will immediately form hydroxides. Now these hydroxides will also act as a sponge for other transition metals that's around it. So in seawater, particle scavenging plays a very important role in determining the concentration of transition metals and rare earth elements. And that is also true for all natural bodies of water. Keep that in mind. Now, let's come back to this system. Two-box model, we're going to work out how this entire thing works. Some of the things to remember: surface ocean has river input, surface ocean has downwelling, surface ocean has upwelling input. The major sink from surface ocean is in the particulate form, where materials are being taken from inorganic form and converted into organic form, and the organic matter is sinking down. And the organic matter can include soft tissue and calcium carbonate shells and silicon dioxide. I shouldn't call it organic matter, I should call it biological matter, because calcium carbonate will never be organic matter. So there is the biological matter, which has two components to it: organic matter, which is a soft tissue, and the calcium carbonate and the silicon dioxide, hard shells. A fraction survives respiration and is preserved in sediments, and most of it is remineralized depending on what sort of element you're working with. Hydrothermal input and output. So the mass budget of water is very simple. If we assume over 1,000-year, well, we don't even have to go to 1,000-year time scale. Over decadal or millennial 100-year time scale, the amount of water in the oceans is not changing. We are not going to consider the melting of the ice caps due to anthropogenic global warming. Okay, on a natural cycle, in a decadal to a 100-year time scale, there is not a large change in sea level. However, what we have done modern day is quite unprecedented. We have started to melt most of the polar ice caps, which means that the total volume of seawater is changing. Salinity of seawater is going down, okay, with very accurate measurements, we can see that the global salinity is going down. Now, surface ocean is precipitation, upwelling, plus river flux. And the total out is evaporation and downwelling flux. The deep ocean is the downwelling flux. The input to the deep ocean is the downwelling flux from the surface ocean. The hydrothermal circulation. The output from the deep ocean is the upwelling flux from the deep to the surface and the hydrothermal circulation. Obviously, these two are equal to each other. They're going to cancel out. And there is no net change in the volume of deep ocean. As it says, hydrothermal circulation is a recirculation system, not a significant source or sink of water from the deep ocean. Now, from that logic, V downwelling and V upwelling has to be the same. So we call it V mix. Okay, so essentially this is the volume of water that leaves the surface goes to the deep and the volume of water that gets upwelled. And with that, we can come to the mass budget of the dissolved components in seawater. Now, all of these mass budgets equations are set up for steady state. Steady state is input equals to output. For a simple element with no net hydrothermal input or output, okay, essentially we can think about all nutrients other than silica. We can write that in the surface ocean we have the upwelling component of the input. This is the upwelling of deep water, the volume of upwelled water, concentration of that element in the deep water. River water concentration times river water flux, which will be equal to surface water concentration times the downwelling flux plus the amount of particulate matter you're going to form. And the deep ocean is far more simpler. The flux of material that's coming in from the surface times the downwelling water flux, and the water has been upwelled out. Now, if we add for the deep ocean, all these other equations are pertaining to the deep ocean. If we add a hydrothermal input component, there will be an input of hydrothermal. And there is a clay removal component given in Cl, which is essentially the orthogenic clay mineral formation. What will be an example of an element like this? Lithium, silica, potassium, calcium. Okay. On the other hand, we can have where hydrothermal circulation is an output for that component. Also, the clay is acting as an output, which will be something like magnesium and sulfur. So the equation will stand out to be this. Please take a note of this, because this is something you will have to do for your final term. Now, one thing I didn't do for the surface ocean here, I didn't do for the deep ocean here, is include the biological term, which we're going to do in the next few sections. Now, since V upwelling and V downwelling are the same, we can replace all the V upwelling downwelling term with V mix. I'm sorry, the V downwelling is still as VD, it should be V mix. So this is all going to become as a component of V mix, right? Now we're going to introduce a few terms. The particulate matter that's falling down, only a fraction of it survives, okay? So that FP, F is the fraction of the particulate matter that survives remineralization. So what gets remineralized is nothing but 1 minus F times P. But this P can also be looked from the perspective of the amount of dissolved component that's reaching the surface ocean. Okay. And the fraction of the dissolved component that's been removed in particulate form. Okay. Why is that important? If I bring in, how am I supplying material to the surface ocean? I'm supplying a dissolved component to the surface ocean either by river or by upwelling. Now, if I remove all of it through particulate matter formation, then the fraction of dissolved component that's reaching the surface ocean that is being removed in a particulate form is 1. So CS becomes 0. So there is nothing of it in the surface ocean. And that's what we see for elements like nitrate, phosphate, even iron and zinc. So that becomes important. So what we're going to do now, we're going to set up a series of equations. We're going to define a few terms. And those terms will be defined based on which of these parameters we know well. If we go back here, we have a good measure of what is Vmix, how much of water is being downwell and upwell annually, how much of river flux is coming into the surface ocean, what is the average river concentration of a particular element. We can measure CS, we can measure CD. That's very easy. Okay. And from that, we can calculate what fraction of these particulate matters are being remineralized, or what fraction of the dissolved load coming to the surface ocean is being transported away in form of particulate matter. So the mass budget of a nutrient under steady state can be written as this. For the surface ocean, we have the supply, which is the upwelling component of the supply. This is the river component of the supply. This is the downwelling component of the supply. Removal, sorry, not supply, removal. And this is the particulate flux. In the deep ocean, we have the downwelling component. This is CS Vmix. This should be Vmix, not Vd. I will update it in the lecture notes when I upload it. And then there is the component of particulate matter that is getting remineralized through respiration. And all of that is being removed as a function of upwelling. Please keep in mind, the fraction of particulate matter that survives respiration has nothing to do with the mass budget of the deep ocean. Because if I take a ball of iron and let it fall through the ocean column, and it doesn't dissolve while it's falling from the surface to the deep, that transport of that ball of iron has nothing to do with the mass budget of the dissolved component in the seawater. The same applies here. The particulate fraction that survives remineralization has nothing to do with the mass budget of the deep ocean. Please keep that in mind. Okay, so this stands for a particular element which has no hydrothermal input or output. Okay, and also we have to keep in note that at steady state, at oceanic steady state, there is no net addition or removal of a particular material from the seawater. So the total inventory of a particular element in seawater remains constant. So which means whatever is my net excess addition has to be the removal flux. So that the flux, which we termed as FP, has to match what is my river input, because other than that, everything is being recycled in the system internally. So the net loss per oceanic cycle, L, is nothing but FP equals to CR/VR. Okay, clear? Now we are equipped with these two equations. That CD Vmix CR/VR equals to CS Vmix, because Vd equals to Vmix equals to Vu plus P, and CS Vmix equals to 1 minus Fp, this. Okay. Now the particulate form is very easy. You can rearrange the equation. Now we introduce the term G. G is the fraction of a given component reaching the surface ocean in dissolved state, which is removed in particulate form. Okay. So G is nothing but P divided by total input. P divided by total input. This is how the equation stands, and from that equation we can rearrange the thing to form an equation like this. From this form, where G equals to 1 minus V mix by V river, sea surface by sea river, the entire thing divided by 1 plus V mix by V river, C deep by C river. We know V mix to V river is a ratio of 300. What we are trying to do is trying to rearrange the equation in a form where we have a few constants and ratios of things that we can measure. Sea surface and sea deep we can measure, and it's going to vary from ocean basin to ocean basin. So we can understand the dynamics of these elemental recycling in different ocean basin by simply looking at the sea surface to sea deep values. Okay. So the G becomes in this form 1 minus 30 times sea surface to sea river plus 1 plus 30 times sea deep to sea river. For an element which is completely depleted in the surface ocean. Let's take phosphate. Phosphate is quantitatively depleted in surface ocean. Sea surface value becomes 0. The entire terms becomes 0. So G equals to 1. Again, what was G? G was a fraction of a given component reaching the surface ocean in dissolved state, removed in particulate form. So this means whatever you supply to the surface ocean is removed in particulate form with a G value of 1. Okay. Now this is what the two-box model looked like in terms of what we are trying to achieve. Now we're going to take it even further. We're going to look at the F value. That is the fraction that is removed, the fraction of particulate matter that is removed per cycle of elemental cycling. We are equipped with these two equations, and we know that the net loss per oceanic cycle is FP or CRBR. And this is what P stands for. So essentially, F times P equals to CRBR. So this is P. So F times P equals to CRBR, or F can be written as this. Again, we rearrange it to look like V mix by V river because that's a component we know has a constant value across the globe. And then what do we need to play with? Sea deep to sea river ratio, sea surface to sea river ratio. So that gives us a form of F equals to 1 by 1 plus 30 sea deep to sea river, sea surface to sea river. Now, why is this form important? If F is a large value, means a lot of the material that's getting into particulate form is taken out from the oceanic cycle as a precipitating organic fraction or a hard tissue or whatever you want to call it. So its removal per cycle is large. So a larger F value means it's inefficiently recycled in deep water, which means it's been biologically pumped out efficiently from the surface ocean to the deep. And thankfully for carbon, that is what we observe. Again, a quick overview. This is what we are playing with: particulate fraction, fraction that survives, fraction that gets remineralized. Okay. Now we have the two components now to play with. G is a fraction of a component that reaches the surface ocean and is removed as particulate form. F is the fraction of particulate matter that survives mineralization. So if we multiply the two components, this is what we get, F times G. F times G is nothing but giving you the material that you're supplying to surface ocean, how much of it is getting in particulate form, and what fraction of that particulate form is surviving the oceanic circle. So essentially, it's the removal of a particular material per oceanic cycle, right? So F times G is how much you are removing out of the system that's been supplied to the surface ocean. And with F times G and with a value for T mix is nothing but the time it takes for the ocean, a parcel of ocean water to sink in North Atlantic and come up in North Pacific, which is like 1,000 years, which we call the mixing time of the ocean. It takes 1,000 years for the oceans to get mixed, which means if you throw a tracer in Bay of Bengal today, from 1,000 years from now, that tracer is going to be very well mixed in the global ocean. So that's what we call the mixing time. So with the value of T mix at hand and with an FG value, we can calculate the residence time of anything as a function of 1,000 by FG in terms of year. What's the implication of it? We're going to compare a couple of elements: phosphorus, barium, and calcium. Phosphorus, we know, is a biolimiting nutrient. Barium has no business being a biolimiting nutrient, but acts as a biolimiting nutrient. Calcium is a biounlimited element, but we have already seen that there is a slight surface depletion of calcium concentration as observed. Okay. F is given by this formula, G is given by this formula. We know V mix by V river is a value of 30. So for phosphorus, these are the values we observe. The sea deep to sea river ratio for phosphorus is 3, and sea surface to sea river ratio is 1.5. For barium, it's 0.3 and 0.1. For calcium, it's 25 and 24.5. And what we can see, the F value for phosphorus is 0.01, for barium is 0.14, for calcium is 0.14, which is quite unique. Why this is unique? F is the fraction of particulate matter that survives remineralization, right? So what a value of 0.01 F means, only 1% of the phosphorus that is being taken up in surface ocean in particulate form survives remineralization. So there is a 1% loss of phosphorus from the surface ocean to the sediment per oceanic cycle, right? G, on the other hand, is giving you the fraction that is remineralized. So the fraction that is remineralized for G stands at 0.95, so 95% remineralization, 70% remineralization, and 0.01% remineralization. This equation doesn't really work well for bio unlimited elements because the difference between sea surface and sea deep is very, very small. From that component, we can calculate T mix from the Fg value, and we can see that the T mix for phosphorus is around 100,000 years, for barium is 10,000 years, and for calcium is around 1,000,000 years. So the two-box model of seawater gives you an overview like this, where we have the biolimiting elements with the surface to river ratio and the deep to river ratio. This is something I'm going to supply you, and I'm going to ask you to calculate the G values, the F values, the Fg values, and the residence time of that particular element in seawater. Now, I'm going to stop here. I'm going to take some questions. Do we have any questions for today's lecture?
So in that slide on you had some terms like REE and all of that. So what are those?
Rare earth elements. REEs are rare earth elements. If you go, do you know which are those?
Yeah.
Lanthanides. In terms of REs, sometimes you will see LREs, HREs, MREs. Okay, it's light, heavy. This is the sort of classification people do. Everybody okay with the two-box model? You have gotten everything, like there is no ambiguity in terms of how things have been remineralized, how the fluxes can be calculated based on simple surface ocean, deep ocean, and river water values. Any questions? No questions, then I'll call it a day. Thank you for attending the class, and if you have any questions, just talk to the TAs, or if it's a pressing question, you can drop me an email. Okay? Chalo, bye-bye. Thank you.
Thank you, sir.
Thank you.